Hi, welcome to this tutorial about electrochemical impedance spectroscopy and how to use it for operando characterization of batteries. The impedance can be considered as the resistance under an alternating electric field. Impedance signals can result also from the relationship between electrical input and response signals, which are sinusoidal, because it is based on the relationship between two wave-like signals. It can be considered a spectroscopy technique. The most common way of interpretation of this technique is by using Nyquist plots to associate the electrochemical system of study to an electrical circuit. In this tutorial, an introduction about electrochemical impedance spectroscopy will be presented, and then later our approach to perform operando measurements will be explained. The impedance can be considered complex, as it can be split in real and imaginary parts. Besides, the mathematical treatments can also have different levels of complexity. What is interesting about electrochemical impedance spectroscopy is the detailed information about different electrochemical processes found at different AC frequencies. These processes can involve, for example, charge transfer, absorption, polarization, or diffusion, and can be used for kinetic studies and for the interpretation of the overall system. The electrochemical systems to study can be also from different application fields, such as surface processes, energy conversion, degradation, and so on. As a practical example, we can compare what is obtained by different electrochemical techniques. The figure on the left is a voltage current curve, from which only the polarization resistance can be determined as a slope from different points or states from the curve. On the other hand, different Nyquist plots can be produced by measuring impedance at different states, so that more parameters from multiple processes can be also obtained. To understand better about impedance, it is good to consider first some basics about electrical circuits, with Ohm's law and Kirchhoff's rules. Ohm's law was providing the relationship between voltage, current, and resistance. Kirchhoff's rules determine the contribution of local voltages and current intensities for resistors arranged in series or in parallel in a circuit. On one hand, at both contact sides of resistors to the main circuit current, different loops are formed with different partial and local voltages. On the other hand, in resistors arranged in parallel, different junctions or nodes are formed with different local current. Kirchhoff's loop and junction rules state that there should be a net balance between local voltages in each loop and between local currents in each junction. Therefore, these partial contributions should suppress each other. As a practical example, the relations between different resistors in an electrical circuit can be determined with Ohm's law and Kirchhoff's rule. In this example of electrical circuit, there is one resistor connected in series and two resistors arranged in parallel. Kirchhoff's junction rule was determining the balance between partial voltages around different sides of a resistor or resistor set placed in series. With Ohm's law, the net balance of local voltages can be also interpreted according to the current intensities and the resistances. Because of the parallel arranged resistors, there are two different partial currents in two loops, so that the net balance of local voltages from the junction rule can be interpreted in two ways. Subtracting these two relations of local voltages according to the intensity current, one of the local voltages and the global voltage can be suppressed, and then one of the local currents can be substituted according to the global current. At the end of the calculation, this can provide the relation of the equivalent resistance for all resistors in the circuit. Once we know about the resistance for circuits with direct current, we can know about impedance for circuits with alternate current. For the case of the impedance, the voltage and current do not have a constant value, but an oscillating variation along time. Therefore, to measure impedance, an alternate sinusoidal signal, like voltage or current intensity, is applied, and then the response signal is measured to determine the impedance as a relationship between them. These oscillations in current and voltage have sinusoidal behavior of certain frequency and amplitude. Additionally, a certain delay between variations of current and voltage can be also present, so that the oscillations may differ by a phase shift. Therefore, alternating current and voltage can be interpreted according to a constant baseline value as DC contribution and a sinusoidal AC contribution of certain angular frequency. In addition, the response might have another phase shift. There are different modes of electrochemical impedance spectroscopy. For potentiostatic measurements of impedance, the voltage is the electrical input and the current is the response signal. For galvanostatic measurements of impedance, the current is the input and the voltage is the response. Sinusoidal signals of coherent behavior can be also considered as phasors with rotatory oscillations, and this results in exponential relations, which provides real and imaginary contributions in complex numbers. Consequently, impedance values are complex resistance values, exponentially dependent on the angular frequency. The response signal will also have a frequency-dependent amplitude and the contribution of the phase shift. Therefore, the resultant impedance will have an impedance modulus for a certain frequency and an exponential contribution of the phase shift, also for a given frequency. Another way to show this exponential relation is by splitting it by the real and imaginary impedances, both frequency dependent. Here it's a comparison of the relations between real and imaginary contributions and modulus or phase shift. Here is a summary of the general equations to interpret impedance, and their visualization provides different plots. For instance, the impedance can be visualized in both the plots according to the modulus or the phase angle upon frequencies. In aqueous plots, according to the relationship of real and imaginary parts for different frequencies. The Lissajous plots visualize the relation between input and response signals for certain frequency points. Noteworthy, the scale in aqueous plots is based on the real and imaginary contributions in logarithmic frequencies, and both the plots are also represented along frequency in logarithmic scale, with the modulus also logarithmic and the phase angle in linear scale. The impedance behavior can change in presence of different electrical circuit elements, and these elements are mainly resistors, capacitors, and inductors. The voltage and current as functions of time can be converted with a Fourier transform into functions of frequency, and this can be applied for each electrical element. For a resistor, the relation of voltage and current is the same in time domain and in frequency domain. Consequently, the impedance resulting from the resistor could be exclusively the resistance itself as its real part, because the phase angle is zero. For a capacitor, the voltage is related to the charge divided by the capacitance. being the charge the integral of the current over time. Therefore, the Fourier transform results also in an inverse imaginary contribution of the frequency and the current. Consequently, the impedance resulting from the capacitor would be a complex value with a negative imaginary part, being the phase angle minus pi divided by 2. For an inductor, the voltage is related to the inductance with the differential of current with time. Therefore, the Fourier transform results also in a proportional imaginary contribution of the frequency and the current. Consequently, the impedance resultant from the inductor would be a complex value with a positive imaginary part, being the phase angle plus pi divided by 2. The visualization of these impedance contributions in real and imaginary parts can already offer an idea about the behavior of these elements in a Nyquist plot. A Nyquist plot consists on the real impedance and the negative imaginary impedance as the axes. For a typical equivalent electrical circuit, a combination of different electrical circuit elements can be interpreted in these plots. An inductance results in a positive contribution of the imaginary part, and typically occurs in the high-frequency region. The ohmic resistance, mostly attributed to solution resistance, is related to a single resistor by the contact of electrolyte and electrodes, and can be represented as the offset of the imaginary part. Next are the RC units, which consists on a capacitor and a resistor arranged in parallel connection. This is related to charge transfer processes, and with some modification can be seen as semicircles. Additionally, the Warburg contribution represents the diffusion and appears as a final tail with certain slope. One of the most important group of electrical elements to interpret in electrochemical impedance spectroscopy are the RC units. As mentioned previously, RC units consist of a resistor and a capacitor arranged in parallel. Referring back to the Kirchhoff's junction rule, the balance of local currents in parallel arranged units can be interpreted in terms of impedance contributions. The resulting calculations provide a characteristic tau term representing a device relaxation time, which consists on the product of the resistance and the capacitance. In a practical example of a RC unit with a resistor of 100 ohms and a capacitor of 10⁻⁵ farads, the phase angle upon frequency decreases asymptotically around the inverse of tau, from 0 to -80 degrees, and the impedance modulus decreases from 100 to 0.1 ohms. Therefore, capacitors at higher frequencies above 1 divided by tau can be considered as good conductors. Analogously to an RC unit, a SARC unit consists of a resistor connected in parallel to a constant phase element instead of a capacitor. A constant phase element differs from a capacitor by having a variable capacitance, and this variation is according to an empirical exponent with values between 0 and 1 to simulate the width of the relaxation time distribution. In the both plot, the higher the exponent, the more pronounced the decrease of phase angle. In the Nyquist plots, the higher the exponent, the more negative the imaginary contribution of the semicircle. Charge transfer processes occur at electrode-electrolyte interfaces of an electrochemical system, and they can be evaluated by electrochemical impedance spectroscopy. Firstly, Faraday reactions result in charge transfer processes by reduced species according to Faraday's law, in which the mass of the converted species is proportional to the flow of charge. For the ideal case of a polarizable electrode, there is no exchange of charge between the electrode and the electrolyte solution, and this system can be expressed with a resistor as the inert electrolyte, connected in series with a capacitor as the electrode, with a rapidly formed double layer. For the case of redox reactions at electrode interfaces, there will be a Faraday current, which can be represented as an electrical element connected in parallel with the electrode capacity. This additional Faraday impedance can be also approximated as a charge transfer resistance if the mass transfer is fast enough to neglect its contribution. For the case of redox reactions at electrode interfaces in which mass transfer of ions has a significant contribution, an additional Warburg element needs to be included in the equivalent electrical circuit to consider the diffusion of ions within the electrolyte solution. The Warburg element implies that the charge transfer is also dependent on the diffusion of the redox active species. The treatment of this element can be more complicated and tedious, and is also described with kinetic parameters of a redox reaction. From the Butler-Volmer equation, the current of Faraday redox reactions can be expressed according to the Faraday constant, the molar equivalence, the kinetic back and forward reaction parameters, and the concentration of the redox species at the electrode interface. The kinetic parameters of the back reaction and the forward reaction can be further calculated in terms of a heterogeneous rate constant at equilibrium potential, and an exponential term with the charge transfer coefficient, the gas constant, temperature, molar equivalence, and the potential increment between electrode and standard equilibrium potential. Therefore, unless there is a voltage applied to the system to create an overpotential, the forward and back reactions could be balanced with each other and there would be no current flow. Another equation to consider for the diffusion processes is the fixed second law. This equation considers the variation of the concentration as partial derivative upon time, the distance to the electrode surface, and the diffusion constant, all for the ion species. With further treatment of these expressions, when solving this for a very small oscillation, changes in voltage amplitude quadratic terms are not significant, and the resulting expressions can be simplified to describe the Warburg coefficient. This Warburg coefficient can be then described according to the contributions of diffusion and concentration at the electrode surface of the different redox species. Consequently, the Faraday impedance with significant contribution of ion diffusion can be then considered as a charge transfer resistance and the Warburg element. This implies that there are both charge transfer and mass transfer at the electrode surface. The Warburg impedance can be expressed for the mass transfer according to the Warburg coefficient and the frequency. The charge transfer resistance, besides, does not depend on the diffusion, but only the concentration of the oxidation species and the kinetic term. These simplified terms can only be obtained under the condition that the charge transfer coefficient and the electrochemical current are from a system in equilibrium. It is also important to note that the Warburg impedance differs from the solution resistance. When comparing both expressions, the behavior according to diffusion is different. This means that the electrode surface is dominated by ions with low diffusion coefficient and low concentration, while the volume of the electrolyte solution is dominated by very mobile ions with high diffusion coefficient and highly concentrated. The representation of electrochemical impedance spectroscopy can be visualized in Nyquist plots by projection of the real and imaginary contributions of the impedance upon logarithmic frequency, analog to a three-dimensional plot. As previously explained, each of these contributions will have different trends of the different frequency points given by the electrical circuit elements of the system to study. For instance, the real part of the impedance can be used to determine the solution resistance at higher frequencies, while the imaginary part of the impedance is more sensitive to changes at certain frequencies and can provide the relaxation times. The resulting Nyquist plots are then suitable to determine the charge transfer resistances of these processes. As an overall view, the different electrical elements in a circuit can provide an interpretation of an electrochemical system, and their distinct behavior can be also distinguished with the different plots. This approach to interpret electrochemical impedance spectroscopy is also known as equivalent circuit model. For instance, we can differentiate an inductance as positive imaginary part, based on the positive phase angle at higher frequencies. The solution resistance can be distinguished as the offset of the negative imaginary part. Then, the charge transfer processes are seen as semicircles in the Nyquist plot, and the Warburg contribution is seen as a final slope at lower frequencies. Once identified the different electrical circuit elements, the respective values can be determined using the features of the Nyquist plot. For instance, the solution resistance is determined as the value of real impedance at the offset of the imaginary part. A charge transfer resistance can be also obtained as the double value of the range of the real impedances from the offset to the maximum point of a semicircle. In the plot of imaginary impedance upon frequency, the relaxation times of charge transfer processes can be determined from the frequencies corresponding to the peaks, and from this the capacitance can be also determined. The other parameters are more complicated to determine directly, but there are also software programs to fit different circuits and provide a more accurate interpretation. As already mentioned, there can be different electrochemical processes at electrode interfaces. In the first case of a polarizable electrode, there is no charge transfer and no Faraday current, so that only the solution resistance and the capacitance of the ion double layer are present. This means that the charges remain in the ions, which are located at the electrode surface, and no electrons are transferred from the electrodes. For the case of charge transfer without diffusion or mass transfer to consider, the charge transfer resistance is arranged in parallel to the double layer capacitance, and this would be equivalent to the phase relaxation processes of characteristic relaxation time. Consequently, for a charge transfer, part of the ions in the double layer will modify their charge by receiving or giving electrons to the electrode, which can also result in deposition processes. With diffusion limited charge transfer, a Randall circuit is proposed, with the Warburg impedance represented by a Warburg element in series with the respective charge transfer resistance. These different electrochemical processes will result in different behavior when represented in the Nyquist plots. For the case of an ideal polarizable electrode, only the capacitance will be observed as imaginary contribution at constant real impedance, which is the solution resistance. For the case of charge transfer without diffusion, a characteristic semicircle results from the capacitor and the charge transfer resistance arranged in parallel, and the offset of this semicircle is the solution resistance. For the case of charge transfer limited by diffusion, the semicircle will also have a tail of a characteristic slope, proportional to the value of the Warburg coefficient. In addition to this, the electrochemical systems can have more levels of complexity to express in equivalent electrical circuits. For instance, the charge transfer can be also limited by an insulation layer at the electrode surface. The insulation layer can be represented by an additional RC unit, connected in parallel to the charge transfer resistance. Another case is the influence of other side reactions to the charge transfer processes, which cause lower presence of ions at the electrode interface. These side reactions usually occur in the electrolyte and can be represented by the Gerischer impedance. These additional cases of electrochemical systems also provide similar behaviors when visualized in the Nacus plots. The charge transfer limited by an insulation layer results in a double semicircle. When the charge transfer is limited by some side reaction, additional semicircles can be also superimposed and elongated. Therefore, sometimes it can be very difficult to interpret correctly the number of different electrical circuit elements. For a simplification of the equivalent circuit modeling, complicated electrical circuits could be expressed as the sum of discrete contributions of charge transfer processes with characteristic relaxation times, represented as void elements of RC units. These void elements could be also expressed according to a continuous combination of the contributions of all processes with distinct relaxation times. Therefore, another way of interpretation of electrochemical impedance spectroscopy is with the identification and quantification of processes according to their relaxation times. This is also known as the distribution of relaxation times and can distinguish different processes at the electrode level. Firstly, a relaxation time can be calculated as a product of a resistance and a capacitance arranged in parallel, which is also the frequency at which charge transfer processes occur. For the evaluation of these distributions, the impedance values can be converted from frequency domain to time domain. Then, the impedance equation is expressed in time domain according to the solution resistance, the polarization resistance, and the different contributions of processes of defined relaxation times. The regularization of this equation can separate and quantify different electrochemical processes. If then, it can be very complex, involving multiple integrals and matrices, so fitting algorithms are also required. The most common one is a Tikhonov regularization, for which the processes have Gaussian distributions around their relaxation time, and the calculated contributions can be used for quantification. In this example of synthetic impedance data, there are 3 RC units and 3 SARC units with constant phase elements. At first, only 2 semicircles are observed in the Nacus plots, but when transferred to the time domain, 6 peaks can be revealed. The first signals are related to the capacitors and represent distinct lines, but the other peaks have distributions of certain dispersion as a result of the constant phase elements. In another example of a void unit, also present in a dummy cell for impedance measurements, the values of resistance and capacitance are known, so that the relaxation time and the impedance values can be calculated. In the plot of the impedance measurement, both simulated and experimental measurements can be well correlated, and the Gaussian contribution can also be visualized according to its distribution of relaxation times. As a general summary about the fundamentals of electrochemical impedance spectroscopy, it can be said that this technique can be used to study electrochemical processes at cell level and at electrode interfaces. And it can also provide complementary information for a better interpretation of a system. The impedance data is usually visualized in Nacus plots, if then there are more plotting possibilities. The most common way of interpretation of impedance data is according to the equivalent circuit model. This interpretation is at cell level, and different electrical units are interpreted, for which the RC units related to charge transfer processes are most relevant. Another possibility of interpretation is by the regularization of the distribution of relaxation times. With this calculation, processes can be interpreted at electrode level, but a regularization algorithm is required. From a different point of view, characterization of a system to study can be ex situ, in situ, or in operando. For ex situ characterization, separated components are only investigated before and after their use in an electrochemical process. This can lead to degradation of the samples during manipulation and to interpretation errors. For in situ measurements, the materials of an electrochemical system do not need to be separated, and the measurements are directly made on the system to investigate. However, if the system is not under working conditions, the properties might differ of what happens in the working environment, that is, during the electrochemical process to investigate. Therefore, operando characterization performs measurements in the system of study during its working conditions, so that the electrochemical processes are occurring while the measurements are being made. On the other hand, electrochemical impedance spectroscopy has some requirements to ensure the validity of its measurements. Such validity can be also evaluated with a validation algorithm. These requirements can also be accomplished under different considerations. For instance, quasi-linear approximation of the exponential voltage-current relation is possible with a small oscillation amplitude of the input signal. For the causality of the response signal depending only on the input, external interferences are avoided by placing the electrochemical system inside a Faraday cage or mesh. Additionally, the stability of the measurement can be checked by repeating measurements, so that similar data are obtained. And for finiteness, the impedance can be fit so that it tends to a constant value. For operando measurements, the stability criterion is crucial, because it means that the electrochemical system should not change with the time. However, when we measure a system under operating conditions, for example during charge or discharge of a battery, the system is continuously changing. This means that the system at the beginning of the measurement would be different than at the end of the measurement. Consequently, measuring impedance in operando conditions could lead to drifts in the measurements, and this needs to be corrected to obtain valid data. These drifts can occur individually for each measurement point at each frequency or cumulative during a whole set of points of a measurement at lower and lower frequencies. The single frequency drifts made with each measurement point are seen in the Lissajous plots when the ellipse is not closed. This happens because the DC contribution of the electrical sinusoidal signals is changing under operating conditions, like charge or discharge. To correct this, the signal is fitted as a sinusoidal function, and then the slope contribution of that fitting function is removed. On the other hand, the time or state drift made along a set of measurements at different frequencies is caused by the accumulated delay time when the different frequency points are measured. In this graph, the values of the real impedance are shown for different measurement sets. And in red, we can see that the time when the points are recorded is deviating more and more from the beginning of the measurement. For the correction of the delay time, a time course interpolation is made by using a dense distribution of measurement sets, so that the points of other measurements at the same frequency can be used to interpolate the impedance values to the time when the measurement was supposed to start. Therefore, a projection of the impedance parameters is calculated as for the initial frequencies at the initial time of measurement. A general way to visualize this combination of drift corrections is with the state coordinates of a changing electrochemical system. First, the hysteresis correction is applied for every frequency point. and then the second state correction is applied for all points. With this, the impedance data should represent what was the electrochemical system at the beginning of the measurement. To prove the validity of the impedance data, it is possible to use different equations for data analysis. The goal is to quantify how valid the data are by calculation of a parameter from the experimental value of another parameter, and then comparing the calculated parameter with its experimental value. The most known validation method is with the Kramer's chronic transforms. If then, the two-pole Hilbert transform can provide some additional advantages. With the Kramer's chronic relations, the real part of the impedance can be calculated from the imaginary part of the impedance and the other way around. For these calculations, integration along an infinite range of frequency is required, so that extrapolation errors are produced. On the other hand, the two-pole Hilbert transform can calculate the impedance modulus from the phase angle. For this calculation, a defined range of frequency can be used in the integral, so that no extrapolation is required. Once calculated the value of the other parameter, the validation can be quantified according to the relative residuals of both values, and this can provide information about the data quality. Here is a more detailed explanation of the two-pole Hilbert transform. The first step is to define the frequency range of the impedance for the integral. The second step would be to integrate the phase angle to the natural logarithm of the frequency along the stated frequency range. The third step would be to take the derivative of the phase angle by the natural logarithm of the frequency and add it to the integral value. The last step would be then to fit the combined expression to the initial impedance modulus and shift it to linear. Ultimately, the calculated impedance moduli can be compared with experimental values by the relative residuals. All procedures to process and analyze operando impedance data can be made with computational calculations and algorithms. The first step could be to read the data files, which could have certain drifts and noise. The second step is the hysteresis drift correction, followed by the time state drift correction. Once done the processing, the next steps are about data analysis, and this includes the regularization of the distribution of relaxation times and the validation by the two-pole Hilbert transform. Last, another consideration is the measurement mode of operando electrochemical impedance spectroscopy. The amplitude of the response signals can exceed the limits at certain frequencies to get a linear response, depending on the measurement mode. For potentiostatic mode, the current is the response signal, and at higher frequencies, the current amplitude is too high. On the other hand, for galvanostatic mode, the voltage is the response signal, and this voltage can exceed its amplitude at lower frequencies. To cope with all frequency ranges, the optimal method would be hybrid galvanostatic mode, which uses AC current and records AC voltage with controlled amplitude. In this last example of experimental impedance measurements of a lithium-sulfur battery, a charge-discharge cycling was also performed. The different processes at different states of charge can be compared for a better study of the system. In addition, multimodal characterization can be also performed by combining impedance with other techniques like X-ray spectroscopy, Raman spectroscopy, or neutron characterization, as well as imaging techniques. For this multimodal characterization, an adapted design of a battery cell is used so that the electrochemical processes can be measured with different techniques. Here, you can find some recommended references to know more about electrochemical impedance spectroscopy. This includes research articles, reviews, and books. And last but not least, you can get our contact information here. This lecture was recorded as part of a joint European project about operando metrology for battery research. This project was supported from an initiative of the European Partnership of Metrology. I hope this was insightful for you, and don't hesitate to contact us.